In the 1970s and 80s, several holes bored into the bottom of the Pacific Ocean by the vessel Glomar Challenger produced samples of sediment that showed that Walter's discovery of superposed and juxtaposed facies also applied to deep-sea sediments. An example from the Grand Canyon is given later. Walter's observations show that facies in sequences superposed and juxtaposed at the same time do not follow the principles of superposition and continuity. This phenomenon, confirmed and explained later on by our experiments in the laboratory, is shown to be a natural consequence of sedimentary mechanics. In 1970, I received a report from the American geologist Edwin McKee of his 1965 observations of sediments deposited as a result of a river in Colorado overflowing its banks at Bijou Creek due to 48 hours of torrential rain upriver. The stratified deposits, reaching a thickness of 12 feet, exhibited particle sorting and bedding planes. Bedding planes are generally interpreted by classical stratigraphy as the result of interruptions of sedimentation and hardening of the surface of the last formed layer prior to further sedimentation. The rains having lasted 48 hours and the supply of sediment being continuous throughout the period, it was impossible by simple observation to tell whether the strata had formed successively one on top of the other. In any case, 48 hours gave no time for the surface of a strata to harden before subsequent sediment was deposited on top of it. So the partings had to be explained by some other phenomenon than hardening. This led me to do some experiments on stratification. The first were in France with limited material. From a preliminary investigation of the existing geological and sedimentological data, I was surprised to find that there was no experimental explanation of the formation of strata. It had apparently been assumed that strata form in accordance with the principles of stratigraphy mentioned earlier, but there was no experimental data to confirm the assumption. My first objective was, therefore, to test the assumption by experiment. If it was shown to be correct, then the experiment would have provided the necessary proof. If the assumption was proved to be incorrect, then the tool used by geologists for determining the chronology of fossils and rocks would be shown to be of little value. The second objective would therefore be to provide an experimentally tested mechanism for strata building. I started by examining how sedimentary particles deposited in both dry and wet conditions. In both cases, sand particles of differing size poured into a flask produced microstrata or laminae. The microstrata formed from the particles of sand sorting themselves out according to size, with the larger particles at the bottom grading up to the smaller ones at the top. This fact was fundamental because it showed that microstrata or laminae formed from particle sorting irrespective of the speed of sedimentation, and not, as had been assumed by geologists for 2 centuries, by one layer forming first and then the next one forming on top of it. The results were published by the French Academy of Sciences and decided me to continue my experiments, but on much larger scale. Larger scale experiments required the resources of a laboratory with the latest technology in hydraulics. Having read their reports on sedimentology, I got in touch with the Colorado State University in North America. This contact led to an agreement being signed for a series of experiments to be conducted in their modern hydraulics laboratory at Fort Collins. This is a photo taken outside the laboratory of myself with Pierre Julien and his assistant. Pierre Julien is a lecturer in sedimentology at the university and was in charge of the experiments. They took place in large glass-walled tanks called flumes. Water, laden with sediment, was pumped into a flume, and the way it deposited could be observed and filmed from above and through the sides of the tank. Different-sized particles of sand were poured into water circulating in a flume. The movement of the water caused the particles to be sorted according to their size. Some of the fine and coarse particles were slowed down by either the roughness of the base of the flume or the sediments already deposited. They deposited, causing superposed laminae to form in the direction of the current. A reduction in current caused mainly larger particles to deposit on the previous laminae. Both the finer and coarser particles not contacting the laterally forming stratum continued to be transported by the current. An increase in the current velocity, again due to friction, caused laminae similar to the previous ones to form on top of the stratum of large particles. The accumulation of sediment between two instants of time, T1 and T2, produced a deposit. The deposit consisted of a part of the lower laminae, part of the stratum of large particles, and part of the upper laminae. Each subsequent individual deposit from upstream to downstream was therefore younger than the one before it. If it were possible to differentiate these successive lateral deposits, the time needed for a strata to form could be calculated by adding the difference of time between T1 and T2 to the difference between T2 and T3, and so on. Due to the presence of a current, strata were formed vertically and laterally at the same time in the direction of the current. The experimenter had scope for testing a wide range of conditions by inclining the flume to provide a slope and by regulating the speed of water current and the supply of sediment. As the results of the various experiments were analyzed, it became clear that what had been demonstrated with microstrata in a flask held good on a much larger scale and under all the conditions tested. The flume experiments demonstrated the mechanical nature of stratification, whereby particles segregated according to their size when transported by a current of variable speed. Desiccation or drying out of deposits caused bedding partings. Stratification of the deposit under both dry and water conditions formed parallel to the slope of the initial area of deposit, which could exceed 30 degrees. The results were published by the Geological Society of France. The discovery that strata form sideways and vertically at the same time, strata form in the same way as sequences of facies, the chronology of strata is measured laterally and vertically, provides probably the most important data to emerge from any experiment in sedimentology. The equally important disclosure was the fact earlier mentioned. When the basic principles of geology had been devised, they amazingly had not taken hydraulic conditions into account. Of course, one strata will superpose upon another when sedimentary particles suspended in still water eventually deposit. As soon as the water is disturbed, superposition ceases because the particles are transported in the direction of the current and sorted according to their size. The first major question was to what extent, if any, could these laboratory results confirm the principles of stratigraphy. Continued experiments revealed corroborating evidence that what was taking place was the normal results of sedimentary mechanics. This basic fact had not emerged because of the conviction that sedimentary deposits were time-dependent. The principle of superposition, believed to account for all stages of the geological column, supported the concept of very slow deposition over long periods of time. Experiments on sediment transported by water with varying currents challenged this concept and showed the limited application of the superposition principle.